Okay, hello everybody. This is Mike here again. So I'm a little late on this podcast. Been trying to do these once a week, but got so super busy at work that I was unable to do the podcast last week, and I think it was the week before. So let me share my screen real fast. Hope everybody's doing well. Okay, this is my continuing series of podcasts on robotics and my feelings on robotics and things going on in the world of robotics. Um, If you want to see my entire presentation on humanoid robots, I'll leave a link in the description to the video. I might eventually have to update the entire presentation on humanoid robots because I'm trying to add more detail, more explanation as to my feelings or thoughts on things. So once again, this is me, who I am, my experience level. You can pause it if you want. I might just do a single quick 10-15 minute podcast about my experiences and my knowledge and so on in the field of robotics and humanoid robots especially. But you can pause the screen and read it if you need to. So let's get back to my presentation and some of the major points that I was trying to explain or to comment on during my presentation on humanoid robots. So I've been trying to add some more detail, trying to think about how to explain my thoughts better. And so I've already done something about durability. So this one, I'm going to focus on giving more examples and more detail about robot actions and are they repeatable and failure recovery after failure, the failure mode of a humanoid robot especially. So one of the reasons why I bring this up is a lot of people who haven't had experience dealing with robotics, doing robot competitions and doing stuff in the field of robots will know that uh, sometimes it's difficult. It's not impossible, but sometimes it's difficult to get a robot to repeat an action over and over and over again without fail. So that's why I want to include repeatability and failure modes with this quick podcast. Um, so I probably should stop sharing my screen just for 1 second here. Okay. The reason why I'm showing you this robot, this is a Spike Prime robot, Lego Spike Prime robot, as you can see here. Now, the reason why I bring up this robot and repeatability is I have so much experience with this and the frustration of a robot not repeating its actions over and over again. So let me kind of explain. So as one of my duties in my day job is that I'm a mentor, facilitator, educator in robotics. And one of the things I do is I help coach two first Lego League uh, robotic teams. And this is the primary robot that we use. And it may not be in this exact configuration with wheels and motors and everything, but this is the control brick and you connect it by Bluetooth or USB and you program it in a the Lego version of Scratch, which is a blocky code. We can get into what blocky code is later. I might try to explain the differences between all the different robot programming language in a future podcast, which might be a pretty cool idea. But one of the issues with this robot is that my first Lego League teams have a competition they do every year where they have a playing surface, a playing mat, and different little uh, projects or different challenges on the mat that they need to perform. And then the robot has to interact with other Lego pieces on the board, moving them around, pushing them around, pulling them up, levers, uh, lots of cool different ways uh, to get the kids to not only use a robot but build attachments for the robot and so on. So one of the problems my kids and one of the huge frustrations for my kids is that they'll program the robot to do to get points by manipulating a Lego structure on their playing surface, and they'll get it to work. But then when they try it again and again and again, they'll have failures. They'll not place the robot in the right starting position. All kinds of little things. So these tires sometimes, uh, can get dirty, or the playing surface can get dirty. Uh, the lighting can be different. So so the lighting affects how the sensors read things, um, and just the motors themselves. These servos right here, they're accurate but not very accurate, and sometimes when you try to get it to do a 90-degree turn, as an example, it will do a 88-degree turn or a 92-degree turn. Now, one of the things that this robot has in it, it has a working gyro inside here. That gyro helps you judge movement on three axes. Up, down, all, X, Y, and Z axis. But this is not, a $10,000, $100,000, $250,000 robot. So the sensor, it's like a couple $1,000 kit. But the sensor itself, it may not be the greatest sensor in the world as far as sampling rate and accuracy goes, which also leads to in your programming environment when you're interacting with sensors, I may do another podcast on this. You have to have some kind of filter so that if the sensor is kicking out extraneous or every once in a while out of bounds information, it's like this and then boom, like this or like this. You gotta you got to try to code for that and use a filter just to keep the regular information coming back from the gyro. Because every once in a while, especially with cheaper gyros, you will have fluctuations outside the bounds of what we should be getting back. So this is what I mean by durability, not durability. This is what I mean by repeatability. And you cannot always guarantee the robot is going to repeat an action, whether it's been AI created or programmed by human, writing the program, because of all kinds of variables. You can try to eliminate many of the variables, but in the end, if you're basing the action of the robot on sensors or its environment, sensors can kick off weird information, or your environment can change. And as your environment changes, your robot can become confused and may not repeat an action over and over and over again. So with a humanoid robot in the factories and the homes and so on, it's pretty obvious. You can see that if your action is not repeated consistently, then you're going to have a failure. Is it a bad failure, or is it just easily get out failure? So if you have a humanoid robot designed to pick something up and move it to another place, you got to make sure that you can, which is the other topic, is it can recover from a failure. So many times with a humanoid robot, when they fall down, they're walking and everything's fine, and then for some reason, there's a environmental issue or a sensor issue causes the robot to fall down. You need to code the humanoid robot to right itself and pick itself up, which again is probably based on a gyro or accelerometer. Can tell that a robot's walking, boom, falls down. The sensor data will say, hey, we're on the ground, we're not walking anymore. get a stand-up move, program it, or have the AI or whatever program a failure. So with AIs and failures, I haven't seen a lot of people talking about AI and failures. Is AI uh, is AI being trained as to what to do if for some reason the gyro accelerometer sensor says that you are no longer walking, you're down on the ground because you slipped, you fell, you ran into something, you ran into somebody. Um, I remember in the DARPA robotics challenge, it's been a while now, almost 10 years now. In the DARPA robotics challenge, a simple act of a humanoid robot trying to open a door created all kinds of problems because if it's trying to open the door, pushes the door out, then you have a little bit of center of gravity issue, balance issue. If the robot tries to pull the door, if the door only opens towards the robot, then the door actually gets in the way of the robot. It causes all kinds of issues. So you've got to be able to program or have the AI adaptable enough so that it can uh, maybe keep a failure from happening, see a failure before it happens. Uh, it feels, so the robot's walking in and the robot starts having whatever issues walking for whatever reason, gyro sensors and accelerometer sensors are kicking back information saying the robot's about ready to fall down, then can the AI get that robot to correct itself before the failure happens? And then what happens if it's a major failure where the robot's now on the ground and there's damage to the robot, maybe there's damage to the legs and so on. What does the robot do? How does the robot overcome that? Do we need human intervention now? Um, so have not heard many uh, people talk about what that failure mode or that failure correction or how the AI is going to handle that situation. Cars are, to me, cars are different than a humanoid robot in the sense that a car can't fall down. Now, a car can get in a crash, but usually what happens when a car gets in a crash, then the car stops moving, maybe notifies somebody and says, "Hey, by the way, I'm in a crash. I ran into something. I should be driving anymore. I need human intervention." So what does that look like for a humanoid robot working in the factory? Especially thousands of humanoid robots working in the factory, and it runs into something, drops something, damages itself, breaks a leg, breaks an arm, breaks a hand, accidentally pushes or shoves something that it shouldn't. All these kind of things are, I think, I really would like to see a little bit more talk about this because that's why I used the Lego example. And I mean, I could probably come up with the other examples. I know that when I was doing robo games and doing Kung Fu and doing some of the autonomous challenges and stuff, uh, things would just happen. Maybe there was, you know, a piece of wood or piece of steel or something, or screw or something on the floor, and the robot stepped on it and then had a failure. Um, so in the autonomous, because usually like in an autonomous competition, you have multiple tries that you can to happen, just like Lego. Uh, with Lego and a lot of robot competitions, you've got two or three chances, and you take the best. You take basically the best run out of the two or three. I know in Lego, it really frustrated my students to be at a competition. They have 2.5 minutes uh, to compete in each competition where they're manipulating on the playing surface, and they can't touch the robot. If they start touching the robot because the robot has failed, then they lose points, and they end up getting frustrated because they keep having to grab the robot and bring it back to the home area and so on. Same thing with the competitions. Sometimes it's like doing Kung Fu. A screw will fall out, or it will hit the seam of the wood of the plane surface, or so on, or just the gyro sensor that was keeping it upright and stable during its walk gets that extraneous or weird signal coming back from it, and they don't have a filter in place, and then the robot will then slip, maybe fall down, and then how to recover that and so on. Um, so I may be just kind of repeating myself now, but it just I'd be interested to see more and more information about repeatability in humanoid robots, especially if you're going to have a humanoid robot working multiple shifts. Um, I've also noticed sometimes with batteries, as the battery gets near the end of its battery charge, then sensor information can be even worse than a normal, just because there's uh, not enough electric power basically for that sensor to be operating. So you got the humanoid robot walking around using up most of the power from the battery, and then near the end of the battery cycle, or the battery's about has lost its charge, yeah, under 10% or so. Sometimes the gyros, accelerometers, and servos and everything start acting a little weird because they're not quite getting enough power to have optimal function. I think that's what I'm trying to say. So again, I feel like this is just something that we're not seeing a lot about. So as far as repeatability and so on goes, I think I don't really have much more of a slides on repeatability. I may kind of talk this one to death, and you bored everybody out. But the big thing with repeatability, a lot of it has to do with your servos, actuators, uh, and how good they are. Because with a humanoid robot, when it's walking around and interacting with its environment, if the servos, for whatever reason, aren't your high-end servos, giving a lot of good feedback and to your program and your sensors and so on, and then what will happen is you'll have a failure. So really good actuator servos are really important. That helps a lot in the repeatability. Also with the Lego robot, I've noticed that if let's say you've got like a little lever that goes up and down and pushes or shoves or flips a switch or something, if your surface area of your tool is so small that if you're off just, a quarter of an inch or 1/8 of an inch or so on. So sometimes just making the your tool wider. Sometimes you can't do this, but if you made instead of making a really slender tool, if you had a really wide tool, especially on a Lego robot, you give it a little more margin for error. A slim tool, you got hardly any surface area, but a larger tool, you got surface area, so you can miss it just a little bit and still flip the switch or move it or whatever what you're trying to do. And same thing with hands and so on. I can talk a little bit more about some of the things I've learned about complexity and so on, and repeat and how robots are built and so on. But I guess what I'm trying to do mainly with this talk is trying to get people to think about that repeatability issue. What do I do? How do I make my robot so that it repeats its actions more consistently? And then if I try to get it as good as I can, and in the end, even if I build in a lot of errors, a margin of errors for the robot, because again, like I said, my Lego kid's always very frustrated about repeatability. Now, my FTC teams and my FRC teams, the repeatability is a lot better because of the actuators, the servos, and the programming. Oh, that brings up something else that I've noticed lately is that one of the issues that the first Lego League team has is that they use a blocky code. Like I was saying, it's very similar to Scratch by MIT. It's Lego's version of blocky code. Um, that's probably not the best code to use for writing robot applications. Something like C or Python or Java uh, can access and use the servo information better, can use the gyros better, can the sampling rate from the gyros can read the gyros better, have more precision, more accuracy. So a text-based language is definitely, I mean, this is probably not going to be an issue with the humanoid robot, but a text-based language is far superior to use when you're programming a humanoid robot. So you definitely will not use blocky code, scratch code for a humanoid robot, which was for my kids who are high school students or junior high school students or grade school students would use for a beginning level robot like this Spike Prime. Um, so just, I mean, I could ramble on and on about repeatability and how to fix a failure. I have not, I mean, I listen as much as I can to people who are building, programming humanoid robots, and I rarely hear about repeatability, repeatability of actions, and what to do if there's a failure. So I kind of hope that gets you thinking and thinking about this topic and how you can engineer yourself, program yourself around it. So that's pretty much it for this one. I hope you found this interesting. I didn't bore you on this, and I hope you see you on my next one. And that should drop this Saturday, so I can get caught back up. I wanted to do this really quick. I'm probably going to talk. There's a lot of things I've been hearing lately about humanoid robots and AI and their complexity. And of course, the social interactions as far as, people, everybody losing their jobs. So I'll come up with just one topic to talk about in my next video, which like I said, it should drop on Saturday. And I hope you found this informative. Hope to see you again and have a good week. Thank you for watching. Oh, kind of slow.